Ladies and gentlemen, my talk will be divided into two parts. First, I will say about the description of turbulence as a stochastic field, and I will tell about the Hopf functional formulation for the turbulence, and about how we try to find a solution of these equations using the external group analysis. The second short part, I will mention the problem of modeling of interaction between such stochastic field and some deformable bundle. So we know that turbulence is described by deterministic Navier-Stokes equation. However, due to dependence on the small variation in the initial and boundary conditions, we can treat turbulence as a stochastic field. So to recall, the stochastic process can be regarded as an extension of the idea of random variable, in the sense that this is additionally dependent on some deterministic variable like time, and the stochastic field is additionally dependent on the space and time. When we treat turbulence as a stochastic field, there is a question how to fully describe turbulence in the statistical sense. And the second, how to model the interaction between stochastic field and some deformable boundary. And here it is performed some work devoted to the interaction between turbulence and the interface between air and water. So in order to describe turbulence, we will use probability density functions. Now the probability that a random variable is contained within a certain bonds is given by this formula here. And however, this PDF is a one-point PDF, and it describes only, it derives only a limited information about turbulence. In order to fully describe stochastic field, we need information, we need multi-point information. So the PDF of many points of the form. Alternatively, we can use the idea of the characteristic function, which is defined as an inverse Fourier transform of PDF. And if we know either characteristic function or the PDF, we can calculate statistics either by differentiation of the characteristic function at the origin or by integration of the PDF. So these are two alternative ways. Now, if you ask how can we describe fully turbulence in the statistical sense, we can use such a graph. We see here on this axis the number of points and here the order of statistics. Now you see that these typical standard turbulence models, they describe, like the viscosity models, describe only first order and 1 point statistic of turbulence, that is the mean velocity. The Reynolds stress model describes the statistic up to the second order. There are also 2-point models or 1-point PDF models which are placed here. We can compute the statistic of any order, at least theoretically, but only also 1-point statistics. So in fact, all the turbulence models, they describe only very limited, this is a very limited description of the turbulent field. Now if we go with the number of points to infinity, and with the order of statistics to infinity, we obtain the full description of Navier-Stokes. And how can this full statistical description be formulated? Either we can consider the infinite number of equations for the multi-point correlation. This is what Professor Waclawczyk was talking about during his lecture. Second possibility is to consider infinite number of equations for the endpoint PDF function. Each time in the equation for the endpoint PDF, we have a term with the n+1 point PDF function, or we can consider only one equation for the so-called characteristic function. This is what I will talk about. Now, the point is that when the number of points goes to infinity, then PDF becomes the probability density functional. So instead of the set of the variables v, we have here a variable v, which is a function of a constant variable x. And in the same sense, characteristic function becomes the characteristic function. Now, statistics, multi-point statistics, can be computed from the characteristic functional by taking functional derivatives. Functional derivatives is sort of extension of the gradient. Now, to stress the difference between description in terms of the Navier-Stokes alone and the statistical description that we use here, I would say that Navier-Stokes describe, given the initial condition, only one realization of turbulent field, whereas Hopf functional equation describes the ensemble averages of all possible solutions. This is the difference. So we talk about description in the full description in the statistical sense. Now, in order, equation for the characteristic functional were derived in the paper of Hopf many years ago. However, this equation is very difficult to treat. So the idea was to extend the Lie group analysis towards such special form of equation with functional derivatives. And I won't go here much into mathematical details of this procedure. The basic idea was to replace the sets of variables by such u, which is a function of the continuous variable x. And also, Lie group analysis allows to find the invariant solution of the equation. So the question was, is it possible to derive such invariant solution for the Hopf functional equation? And as a test case, we used the Berger's equation in Fourier space. Not the Navier-Stokes. The Berger's is considered as a tone model of turbulence somehow. So it is easier, there is no pressure, and this is only one-dimensional. So this was the reason for taking this equation first in this mathematical procedure. And this is the Hopf functional formulation of the Berger's equation. So we applied the extended Lie group analysis to these equations, and after some calculations, it was possible to obtain two meaningful solutions. And the first one has such form. The characteristic functional is described as a sum of constants, which has such form. And here we recognize the 1/t decay of the Southwood profile. Also, we obtained a solution for the viscous case, which was also comparable to some other works on the Berger's equation. So it means that this analysis gives us some insight into the phenomena that we investigate. I only shortly mentioned the second area of research is connected with the interaction between turbulence and the electromagnetic boundary, where in most of the approaches only the mean position of the interface is considered. In this approach, we try to describe the position of the interface by intermittency function, which describes the probability that the phase k is present at a given point in time t. And we proposed a model for this intermittency function. This is now ongoing research under the PhD grant. So to sum up, I was talking about new mathematical method applied to another formulation for the turbulence, and about how this big group analysis can help us to find some insight into the, to gain some insight into the phenomenon described by equation, and mention also modeling interaction between turbulence and the lambda.
Thank you very much. The talk is open for questions.
Small question. How you predict the deformable surface? Yeah.
How you predict the deformable surface?
Yeah. Variable surface.
You mean numerically? I mean, the idea is in this type of modeling, the idea is that actually the formation of if we consider the turbulence inside in a fluid and how it influences the interface, and then it depends very much on the intensity of turbulence and the length of the eddies of the turbulent eddies. And now we want to describe this interface not as a new line only, because there are in fact there are deformations due to these turbulent eddies, but by some smoothed function. It will be done, if you ask about numerical procedure, it will be done within somehow similar method to the volume of fluid approach, but smoothed for the not sharp, the function is not sharp, will be not sharp, but somewhat smoothed. So this is the numerical procedure we want to use.
Okay, I guess we have to stop here. But thank you again. So our next speaker will be